Today we are going through Physics 062543 May June paper 2021. Question number 1 says Figure 1.1 shows a load suspended from a spring. The value of spring constant K is 0.20 newtons per centimeter. The spring reaches its limit of proportionality when the load is 15 newton. Part A says calculate the extension of the spring when the load is 3.0 newton. So we know the formula F equals kx, and we know F, which is 3 Newton. We know K, which is 0.20 Newton per centimeter. So we can rearrange our formula to get X. We get F by K. Then we can put in our values 3.0 divided by 0.20, and when we use our calculator we get 15. So our extension is 15 centimeter, as they're using centimeters over here. Okay, explain what is meant by the term limit of proportionality of spring. So we can just write down the simple definition of limit of proportionality, which is going to be when the extension of spring is proportional to the load applied on spring. As the limit is exceeded, the spring won't return to its original form. It's better to memorize this definition. They usually ask this for 1 or 2 marks, so you have to write the same thing for every single definition. Part C says on figure 1.2, sketch an extension load graph for a spring. Label the limit of proportionality with the letter L on your graph. So they told us in the first part that the limit of proportionality is reached when the load is 15 Newton, right? So we can draw our graph, and we know that extension is going to be proportional to the load before the limit is exceeded. So it's going to be a straight line till 15 Newton of load. As soon as 15 Newton of load is reached, the limit of proportionality is exceeded, and we get our graph like this, which is going to be curved towards up. So the extension, the simple explanation for this is going to be when the limit of proportionality is not exceeded, 1 Newton of weight is going to give us 1 centimeter of extension, and when the limit of proportionality is exceeded, 1 Newton of weight could give us 2 centimeters of extension. That's why the curve is towards up. And we can mark our L here. So we are done with this part. Part D says the load is applied down a small distance below its equilibrium position to position A, as shown in figure 1.3. The load then moves up and down between position A and position B. So there's an equilibrium position here, which is approximately here. We can label this as E. Now we know that the velocity of the load at position A is going to be 0, at position B it's going to be 0, and at equilibrium position it's going to be maximum. So the question says describe the energy transfers which occur as the load moves. from position A to equilibrium position. From position A, at position A there is zero velocity, that means kinetic energy is zero, and at position E the kinetic energy is max. So what occur during these positions? We can write down here that from elastic potential to kinetic energy, and for the second part we can write the same thing, which is gonna be opposite. So from the equilibrium position to B is gonna be almost the same thing. It's gonna be from kinetic energy to potential energy, because at position B the velocity is zero, and we know that a kinetic energy has the formula of half mv square. When v is zero, our whole equation becomes zero, that means kinetic energy is zero. So we can write here from kinetic energy to potential, elastic potential. And we are done with first question. Question number 2, part A says figure 2.1 shows a bookshelf with two groups of books A and B on it. There are 6 books in each group of books. All books are identical. The mass of each book is 0.52 kg. Part I says explain why the pressure exerted on the shelf by books in group B is less than the pressure exerted on shelf by group A. So we know the formula P equals force divided by area, and according to this formula pressure is inversely proportional to 1 by A. So as area increases, pressure should decrease, and we can see here the area of group A is less, so that means the pressure should be more, and the area for group B is more, so that means less pressure. So we can write here that P is inversely proportional to A, as area in contact with the shelf increases, pressure decreases. And we know that we have 6 books on this side and 6 books on this side, so the force applied by each group is going to be same. And you get 3 marks for this. Part 3 says calculate the pressure exerted on the shelf by the books in group A. Alright, so we know that the formula is pressure equals force divided by area. We can find out our force and we can find out our area. So our force is going to be 0.52, which is mass into gravitational constant. So 0.52 into 10, which is going to give us 5.2. So our force is 5.2 Newton. And our area is going to be, for group A, it's going to be 1.3 centimeter into 2.1 centimeter. The reason we don't take 30 centimeter is because it's not in contact with the shelf. If we were to take for group B, we would take 30 centimeter and 21 centimeter, because this 30 centimeter and 21 centimeter is in contact with the shelf. So we're going to take 1.3 into 10 raised to the power minus 2 because it's in centimeter and we have to convert this into meters, and 21 into 10 raised to the power minus 2. We can find out our value of area, which is going to be 1.3 into 10 raised to the power minus 2 and 21 into 10 raised to the power minus 2, which is going to give us 2.73 into 10 raised to the power minus 3. So this is our area and we have the force. To find out the total pressure, we multiply this force by 6 and this area by 6 because we have 6 books, and we can write our numbers in the equation, which is going to be 6 into 5.2 divided by 6 into 2.73 into 10 raised to the power minus 3, and eventually this will cancel out, so we are going to get 5.2 and then divided by 2.73 into 10 raised to the power minus 3, and which is going to give us our answer as 1904. We can round it off to 3 significant figure, which is going to be 1900. So we can write 1900 Pascal. Part B says a diver dives to a depth below the surface of the sea, where the total pressure is this, the atmospheric pressure is this, the density of the water is this. Calculate the depth of the diver below the surface of the sea. So we know the formula that pressure equals H rho G, and we have total pressure, which is 3.0 into 10 raised to the power 5. We have atmospheric pressure, which is 1.0 into 10 raised to the power 5, and we have density, which is 1030, and we can find out our H by rearranging this equation: pressure divided by density into gravity, and our gravity here in this case is going to be 10, so pressure is going to be change in pressure, which will be 3.0 minus 1.0 into 10 raised to the power 5 divided by the density, which is going to be 1030, and then we multiply by our gravity. So we get our answer as 1030 into 10, which will give us our answer as, oh, it's 10 raised to the power 5, not, we have made a small mistake here. It's 10 raised to the power 5, so it's going to be 19 meters. This is not minus 5, it's 10 raised to the power 5. So it's going to be 19 meters. We can write 19 and then don't forget the unit, which is going to be meters. And we are done with question number 2, part B. Question number 3, a car travels at a constant speed v on a horizontal straight road. The driver sees an obstacle on the road ahead. Part A says the distance traveled in the time between the driver seeing the obstruction and applying the brake is thinking distance. Explain why the thinking distance is directly proportional to v. We know the formula that speed equals distance divided by time, and the thinking time is constant. It doesn't matter if you change the situation or anything, the thinking time is going to be constant for every single experiment. So that's why our equation is going to become S into S is going to be proportional to D because T is constant. When T becomes constant, our S is going to be proportional to D. So we can write here that thinking time is constant Therefore, S is directly proportional to D. Part B says when the brakes are applied, the car decelerates uniformly to rest. The frictional force applied by the brake is constant. The distance traveled between the first applying the brakes and the car stopping is the braking distance. Explain why is braking distance proportional to v square. So we know that work done to stop the car is going to be equal to the kinetic energy, right? Only then the kinetic energy is going to be equal to 0. So we can write here kinetic energy, which is half mv square, will be equal to work done of the force, work done to bring the kinetic energy to 0. So both of them are going to be equal. Half mv square is going to be equal to F into D, and from this equation we can see that V square is directly proportional to D. So we can write here V square is directly proportional to D because of this. Part C says the car is traveling at 22 meters per second. The thinking distance is 15 meters. Calculate the time taken to travel the thinking distance. So we know the formula speed equals distance divided by time, and we know the distance is 15 meters. Time we need to find, and velocity is 22 meters per second. So we can rearrange our formula. So if we rearrange our formula, T equals D by S, and we have D, which is 15 meters. We have S, which is 22 meters per second, and this is going to give us 0.68. So we get our time as 0.68 seconds. Part 2 says the car has a mass of 1400 kg, 1400 kg. The time taken for the car to stop after the brakes are applied is 2.1 seconds. Calculate the force required to stop the car in this time. So the equation which relates this question is F equals ma. We know mass, which is 1400, and we can find out our acceleration by v by t. By the formula, acceleration equals v by t, and so acceleration is going to be equal to v, which we have is 22, which was given in the first part, which is here 22 meters per second, and t is 2.1 seconds, which is given in this part. So we can find out our acceleration, which is going to be 22 divided by 2.1, which is 10.5. And we can find out our force now, which is going to be mass into 10.5, which is going to give us our answer as 14666, which is 14,600, or we can round it off to 15000, and this is going to be Newton. And we are done with question number 3. Question number 4 says define specific latent heat of fusion, and we can write our definition of specific latent heat of fusion, which is energy transferred 1 kg of unit mass freezes or melts. Part 2 says a cup of water contains 250 centimeter cube of water at temperature 0 degrees Celsius. An identical cup contains 250 meter cube of mixture of ice and water at temperature 0 degrees Celsius. Temperature of surrounding is this, which is 20 degrees Celsius. Explain which cup contains the liquid with the lower temperature after 10 minutes. So we can draw here. We have a cup with water and we have a cup with water and ice. So of course, for this cup, energy is going to be needed to convert this ice into water. And for this cup, we don't need to change anything other than the water. So the energy is going to be needed for water. And the temperature of the water is going to go down. So our answer for this is simply going to be cup of mixture ice and water. And the reason for this is going to be energy is needed for changing ice. Therefore, the temperature does not change. And this is going to be our answer for question number 4, part 2. Question number 4, part B says that on a hot day, sweat from a person's skin and then it evaporates. Sweat forms on a person's skin and then it evaporates. Explain in terms of molecules how the evaporation of sweat cools the person. So, for example, this is our skin, right? This skin. And we have water molecules on this. And after that, what happens is we have high energy molecules on the top. So they leave the surface of the water and the water becomes cooler. So this water becomes cooler. And eventually what happens is after some time, all the high molecules with kinetic energy, high kinetic energy molecules will leave the surface of the water and the water is going to become cooler. So that's why the person's skin also becomes cooler. So we can write our explanation here that during evaporation, high kinetic energy molecules leave the surface of water. And then what happens is remaining liquid water becomes cooler. Then what happens is thermal energy is transferred from person to the water, making the person cooler. And this is going to be our answer for 3 marks. Part 2 says explain why this process is more effective when a wind is blowing. So the simple explanation is going to be there will be faster evaporation as wind blows fast molecule. Evaporation as wind blows fast molecules. And we are done with question number 4. Question number 5 says figure 5.1 shows a wave on the sea approaching a harbor. Part I says draw 3 lines wave crest in the harbor. So what happens is here it's gonna be same approximately, and then it's gonna start to diffract as it goes out, and the distance between the waves should be same. Like this. So make sure that the distance between these wave crests and these wave crests is same, all of these, and it should be diffracting outwards. Part 2 says another harbor has a much wider gap between its walls. Describe and explain how the pattern of the wave crest in this harbor is different from the pattern you have drawn in I. So for this we can draw another harbor wall, which is gonna be like this. Now what will happen here is the wave will pass through here, and then there will be little or no diffraction here, and then the wave will just continue like this because there's not enough small gap to for the wave to get diffracted. So we can write here our answer: wave passing through the gaps remain same, or we can say it straight. And the explanation is going to be because the gap is too large for the wave to get diffracted. Part B says a sound of wave frequency this travels through a seawater. The speed of sound in sea is this. Calculate the wavelength of sound wave in seawater. We have the formula which is V equals F lambda, and we're given with frequency. We have the speed which is 1500, and we have the frequency which is 850. What we can do is rearrange our formula. V equals F lambda, and we have to find the wavelength which is lambda. So we get lambda equals V by F, and this is going to be our equation. So we can put in our values, which is going to be lambda equals V, which is 1500, divided by the frequency, which is 850, and we can put this in our calculator, which is going to give us 1.76. And this we can round it off to 1.80. So wavelength is 1.80, and we are supposed to write the units as well, which is going to be meters. And we are done with question number 5. Question number 6. Figure 6.1 is a full-scale diagram of a lens and an object O. Part A says the focal length of lens is 3.5 cm. On figure 6.1, mark and label with the letter F the positions of two principal focuses. So we can take our ruler and measure the distance 3.5, which is going to be here, and 3.5, right? It's going to be somewhere here. And another 3.5, which is going to be here. Make sure to take the distance from the center here. Okay, this is the center. Make sure to take the distance between this and this. So that will give you your distance. And we can label this as F. Part B says on figure 6.1, draw 3 rays to locate the image. Draw an arrow to represent the image and label the image as I. So we are supposed to use 3 rays, and we can use our ruler to draw a straight line here, which is just gonna pass from here, and a line which passes through focal length. It's gonna be somewhere here. This line is gonna pass through the focal length. This is gonna pass straight through it, and our image is gonna form somewhere here where the two rays meet. So we can write I here, and as they're saying 3 rays, we have to draw one more ray which is gonna be passing through the center here, and this will complete our diagram. Part D says a student incorrectly states that the lens is being used as a magnifying glass. Part D I says state how the image produced by a magnifying glass is different from the image I. So the 3 properties. Part C says state 3 properties of the image I. So the image I is, as you can see, is inverted. So we can write here inverted, which is going to be our first property. Then the second property is going to be it is enlarged. When you draw a full scale diagram, you can see that the distance between this and this is going to be different, so it is enlarged. And the third point is going to be it is a real image. Because as you change the distance from here, the distance will change here as well, and it's a real image. It's not a magnification. Part D I says state how the image produced by a magnifying glass is different from image I. So in magnifying glass, what happens is that the image will be produced upwards here, and it's going to be enlarged. So this is going to be for magnifying glass, where the image is produced on the same side of the object. So we can write here image produced by a magnifying glass is upright, and we get 1 mark for this. Part 2 says a student moves the object O to position P so that the lens shown in this acts as a magnifying glass. Mark a possible position for P. So for this object and so for this lens to act as magnifying glass, the object should be between this distance, between the focal length and the lens. So the object should be in between this. So we can just write here or mark the position P here. If you learn the properties of magnifying glass and lens, you know that the distance, the object should be in between the focal length and the lens for the lens to act as an magnifying glass. And we are done with question number 6. Question number 7. Part A says define electromotive force. And we can write our definition for electromotive force, which is energy supplied to derive a unit charge. And you get 1 mark for energy supplied, and you get mark if you mention a unit charge. Part B says figure 7.1 shows a circuit, and we have a battery which has 12 voltage of PD. The two lamps are shown are identical. Each lamp has a potential difference of 3.0 across it and a current of this. A length of uniform metal wire. The resistance of PQ is R. So the resistance of PQ is R. And we know the current is 2.1 or 2.0 ampere. And each of the lamp has 3.0 potential difference. Part I says calculate the value of R. So for calculating the value of R, we know the formula V equals IR, and R is going to be potential difference divided by the current, and the potential difference here is going to be total potential difference minus the potential difference in the lamp, which is going to be 12 minus 3, which is 9, and the current is going to be adding up here, which is going to be 2 plus 2, which is 4 ampere. So we got our potential difference and we have our current. So our potential difference is 9 and our current is 4, and we can find out a value which is going to be 2.25, which is approximately equal to 2.30 ohms. Don't forget to write your units. Part 2 says another piece of wire is made of same metal as PQ. The length of the new piece of wire is twice as the length of PQ. Okay, so the length we know is twice. The diameter of new piece of the wire is twice the diameter of PQ. So this question is a little difficult, and I'm going to explain you with this new type of method, and you have to bear with me to understand the whole thing. So what we have is we're going to be using R equals resistivity into length divided by area. Okay, so the information we are given in the question is R1. We found it in the first part. We found out in the first part, which is 2.30, and we know that the length of the wire PQ is going to be L, and the radius is going to be D by 2, and R2 is we are supposed to find, and length in the question it mentions that it is 2L, which is twice as the length of PQ, and this we're writing is for, let's say, RS. Okay, so the radius is gonna be twice as the radius of the first one, which is going to be d by 2. So this gets cancelled, and this is going to remain as d. If you plug in our values, we get 2.30 equals resistivity into length divided by area, which is going to be pi r square, which is going to be d by 2 square. Next, what we have is for rs, we're going to have r2 equals resistivity into 2l divided by pi d square, because r equals d in the second case. So the thing we can do here is we can take out the 2 and we get pl divided by pi d square. And if we find out our value of resistivity into length divided by pi d square, we can just substitute it here in this equation and get our value of r2. So for that, we do is 2.30, which is going to be equal to resistivity into length divided by pi, and this is going to be same as d square divided by 4, and this 4 goes up, so it becomes 2.30 equals 4 pl divided by 4 pi d square, and we can take 4 as common outside, so pl equals pi d square, and we can divide everything by 4 to get the value of resistivity into length divided by pi d square. So this will divide by 4, this will divide by 4, and we get our value of pi d square, which is going to be resistivity into L pi d square equals 2.30 divided by 4. And we can just substitute this value here to get our value of R2. So we get R2 equals 2 into 2.30 divided by 4, which is going to give us our answer as 2 into 2.30 divided by 4, which is going to be 1.15, which we can just round it off to 1.2. And we can write our answer here, 1.2 ohm. I know this is a lengthy part for 3 marks, but you have to do this. Just watch the video again if you didn't understand. Try doing it by yourself and hopefully you'll get it. And we're done with this question. Question number 8, part A. State the difference between analog signal and digital signal. You might draw a diagram to explain your answer. So when they say you may draw a diagram, you have to draw a diagram. Okay, so the thing we can do is we can draw here digital signal, and here we can draw as analog signal. And we're gonna have here is our analog signal, which is gonna be same as sine curve. And for digital signal, we can draw as bunch of ones and zeros, which is gonna be like this: 1 0 1 0 1 0, and make sure to label this as 1 and 0. So for the explanation, we can write here as digital signals only have 1 and zeros. Analog signals have any value. because maybe at this point it's this, at this point it's this, at this point it's this. It's not a fixed value. But for digital, we only have 1 and 0. Part B says draw the symbol for NOR gate. And as you know that for NOR gate, it's going to be not OR, and it's going to be like this, 2 inputs, and a normal NOR gate. And then for NOT, we're just going to draw a circle here, and then we're going to give the output. And we get 1 mark for this. Part C says figure 8.1 shows a combination of logic gates XYZ. The gates are not represented by the standard symbols. So we are supposed to find out the output F. And part I says from table 8.1 deduce the name of the logic gate X. So we can see here when the inputs A and B are given, the output is D. So we can check here in this table A, B, and the output is D. So when 0, both inputs are 0, the output is 0. When both inputs are 1, output is 1. Here also you can see when both inputs are 1, output is 1. So this is an AND gate, because for AND gate, when both inputs are 1, the output is 1. And for logic gate Y, it's gonna be, okay, the inputs are D and C and the output is E. So we can check from here. The input is D and C and output is E. The easiest way of doing this is checking when does the input give you 1 as the output. So you can see here that when either of them are 1, it gives us output as 1. So it should be OR gate. It's going to be OR. Part 2 says logic gate Z is a NAND gate. Complete the column F of table 8.1. So for NAND gate, we know that it's going to be opposite of AND, and we can write the table for AND here, which is going to be our 4 inputs 0, 0, 1, 0, 0, 1, and 1, 1. The only output which is going to be 1 is going to be the last one, and the other outputs are going to be 0. So for NAND, it's going to be opposite of this thing, which is going to be 1, 1, 1, 0. So when both inputs are 1, the output is 0. So we can see here both inputs are E, so we have to check E from the column, and both inputs are 1, so 1, 1, 1, 1. The output is going to be 0. So it's going to be 1, 1, 1, 1. And this is how you put the table. The rest of the things you just write 1 and then you're done with the table. And we finished our question number 8. Question number 9. An X-ray machine requires a supply of this kilovolts. The remains electricity supply is 230 volts. A transformer is used to supply correct voltage to X-ray machine. There are 50 turns on the primary coil of the transformer. Calculate the number of turns on the secondary coil. So we know the formula NS divided by NP, which is going to be equal to Vs divided by Vp. We are given with Vs is going to be 110 into 10 raised to power 3 volts, and Ns we are supposed to find, we don't know this. V, voltage of primary, is 230 volts, and the number of turns in primary coil coil is 50. To find out the value of Ns, we can just rearrange our formula, and we get Vs divided by Vp into Np, which is going to give us the value of Ns, number of coil in secondary. So Vs we know as 110 into 10 raised to power 3 divided by Vp, which is 230 into Np, which is number of coils in primary coil, number of turns in primary coil. So it's going to be 50, which is going to give us the answer for number of turns in secondary coil. So it's going to be 50 into 110 into 10 raised to power 3 divided by 230, which is going to give us our answer as 23,900. We can just round it off to 24,000, and we don't have any unit for number of turns. Part B says draw a label diagram of a step-down transformer. On the labels, state a suitable material of each component. So we can just draw a transformer here. It's going to be a square, and then there's going to be another square here. And as it's a step-down transformer, what will happen is number of turns in primary coil will be more as compared to the number of coils in secondary coil. And this is going to be made up of iron, so we can just write this as iron core. These are going to be copper wires, and even this is going to be copper wire. And we are done with the drawing, so we can move on to the part C. Explain how a transformer operates. So how does a transformer operates is alternating current is applied here on this side, and this is how you label alternating current. And when the alternating current is applied, what happens is there is a change in magnetic field over here, and what happens is this magnetic field, let's draw this as light blue. This magnetic field interferes with the magnetic field of this coil. So what happens is we get induced EMF on this side. So we can just write down here, when AC voltage is applied in primary coil, there is change in magnetic field in the secondary coil. Therefore, voltage is induced in secondary coil. And we are done with question number 9. Question number 10. Part A says figure 10.1 shows a beam of radiation in vacuum. The beam contains alpha particle, beta particle, and gamma rays. The beam contains alpha particle, beta particle, and gamma rays. Here we can read the diagram. It says region of uniform magnetic field out of the paper. So as it is out of the paper, it's going to be a dot. a beam of radiation is going here containing alpha, beta, and gamma rays. The beam enters the region where there is a strong uniform magnetic field. The right direction of the magnetic field is out of the page. Mark and label the paths through the magnetic field of alpha particle, beta particle, and gamma rays. So um, as alpha particle is positive, beta particle is negative, and gamma rays don't have any charge, they're neutral. So we can write here positive and beta particle is negative and gamma rays are neutral. So what will happen is gamma rays will not get affected by anything, they'll just pass through. So we can just draw a straight line here, which is going to be for gamma rays because they don't get deflected. As we use Fleming's left hand rule, we can see that the direction of motion is this, which is towards right, and um, the magnetic field is coming outwards. And if you see the direction of your thumb, it will show you that the force is towards down here, and this is going to be our B. So we know that as alpha particle is positive, the force is going to be down on it. So we can write this as alpha particle, and for beta particle it's going to be opposite of alpha particle. It's going to be same as this beta particle. The path is going to be same, but then it will be inverted because it's negative. Part B says radioactive sources have many uses in medicine. State 2 safety precautions which hospital staff take when working with gamma ray sources. The safety precautions which should be taken is store gamma ray in lead line boxes. As we know that gamma rays cannot pass through lead, so keeping gamma rays in lead line boxes will make sure that they don't just go and pass through and get absorbed by humans. So for second point we can write is we can hide or stand behind shield provided. And this is going to be our answer for part 2. Question number 10, part C says the radioactive isotope iodine 3131 is used as a tracer in medicine diagnosis. A nucleus of iodine 313 contains 53 proton and 78 neutron. The symbol for iodine is I. Use nuclide notation to show the isotope of iodine. The way how nuclide notation works is that here we will give the symbol, and here is going to be the mass number, and here there is going to be atomic number. So we can write our nuclide notation here now, which is going to be I, and then our mass number is going to be 131, and then our atomic number is going to be 53. So this is how we write nuclide notation for the isotope. Part C2 says iodine 313 emits gamma radiation. It has a half-life of 8 hours. Explain why this emission and this half-life makes iodine 313 a suitable material for a tracer in medicine diagnosis. So as we know, there should be some time for the radiation to get detected, and as it is gamma rays, So it can be detected outside the body, outside the body, can be detected outside the body, and it has a short life enough to not cause any harm to human body, as gamma radiations are highly ionizing, passes through human body without harming. So we can write here our explanation. Gamma rays can be detected outside the body, has half-life long enough to be detected, and we can write our last point is that gamma rays emitted pass through human body without harming, and this will be enough for you to get 2 marks. And we are done with the last question. I hope you found this video helpful. Do subscribe, like this video, and comment down below if you have any questions. I'll respond to you as soon as possible. See you in the next video.